Hello, Rouse. For lesson 3.6 and its sort of continuation, 3.6.5, let's just do another function together. Let's sketch a function. I think it might be from a homework sheet somewhere, so I don't think I just made it up myself, but it's okay if we get another run through it. Let's sketch f of x equals x minus the square root of x. We'll label intercepts, critical points, inflection points, and asymptotes. I want you comfortable with these directions. This doesn't necessarily mean that there are any intercepts, critical points, inflection points, or asymptotes. I've seen students with a touch of the OCD stare at a question like this for 20 minutes saying, I can't figure out where there's an asymptote. Well, then you don't have to label any. Okay, I don't know if we really need to make use of our advanced functions combination of functions approach here, but it might be useful to think about that first. If you have g of x equals x and h of x equals, I think I might think of h of x as that right there, then you can say that f is g minus h. And where this might be useful is for a difference of functions to exist, you need both of the functions to exist, right? So here's g, here's h. Notice that h only exists when x is greater than or equal to 0. So that means I'm not allowed to subtract something by something that doesn't. I can't subtract g by an output that doesn't exist on h. So it's sort of like the what did we call it? I think it was the intersection or the overlap of your domains of your two functions becomes the domain of the difference of your functions. I'm going to start with that then. Because this will tell me to throw out any critical numbers or inflection numbers that are outside of the domain of the function. The domain of f is going to be the set of all x values such that x is greater than or equal to 0 and x is an element of the real numbers. But that'll also help me sort of scale my sketch a bit. I'm wondering if I could then predict as well here that, I mean, at this first possible input from h, f of 0 is definitely going to be 0. I mean, we can see that from just finding the y-intercept. F of 0 is going to be 0 minus the square root of 0. That's 0. Cool. So we go through 0, 0. That's also, I think, our only root. Oh, no, we've got another root here. Are we going to find the location? Yeah, we'll find the location at that point. That might be visible to us, actually, if we think about what our line y equals x and y equals the square root of x look like together. Isn't that 1, 1? So wouldn't I expect this to be at a height of 0 when x equals 1? We can figure that out by going to the function and finding the x-intercept. Let's do that, or sorry, the x-intercept by going to factored form. Now to put this into factored form, it's not really a polynomial function, is it? But using our old skill of removing the common factor, the greatest common factor, treating it as the power with the smallest exponent, will work just fine here. I have an exponent of x to the exponent 1 here. X to the exponent 1/2 times what gives me x to the exponent 1? That's x to the exponent 1/2. It doesn't tidy up as well as some other functions have for us. But if I write it as the square root of x times the square root of x minus 1, I think I can find my roots at x equals 0, maybe obviously. And I get another root when the square root of x minus 1 is equal to 0. That happens when the square root of x is equal to 1. And that happens when x is equal to 1, squaring both sides if you like. Yep. So now we've got all of our intercepts. We've got our y-intercept and we've got our x-intercept. And we're good to go. Let's look at the first derivative. And for the first derivative, why don't we go from like this line right here? I figure differentiating from there is probably going to be easiest. You could even tell your reader that we're working from asterisks. Because, I mean, you're starting here. Imagine you have this function and you've manipulated it. You don't need to use the product rule to differentiate this function. Go back to when it wasn't a product. F prime of x, make sure your functions are always labeled, is going to be, let's see, derivative of sums is easy, minus 1/2 times x to the exponent negative 1/2. And maybe I'll label this as, I might have to, let's call this asterisk 1. So I think I'm going to label this asterisk 2 and work back from here a little bit later. For an analysis, I kind of feel like writing this with natural exponents will be a little bit easier. 1 divided by 2 times the square root of x. And what do we notice here? Here's one of the things I like about this function. We have 2 different types of critical points. Notice that 0 is not an element of the domain of f prime, but 0 is an element of the domain of f. And therefore, I'm going to predict that we have likely a vertical tangent when x is equal to 0, or in other words, at 0, 0. Okay, I'm not seeing a jump discontinuity occurring here, but I'd notice that f prime of 0 is not going to exist. You can't do 1 minus something that doesn't exist and say that it's just going to be 1. It doesn't work. Let's look for roots. Not of f anymore, but here, let's specify this as the roots of f, and these are the roots of f prime. You don't need to say I'm setting f prime of x equal to 0 now. You're saying I'm looking for the roots. Let's solve this equation. And it's not as complicated as it might look. I'm gonna, I don't know, add 1 divided by 2 times the square root of x to both sides. I'll multiply both sides by, how about just the square root of x? There's no need to use cross multiplication here. Get out of here. And then square both sides, and I get x equals 1/4. So this is another critical number. 1/4 is a root of the derivative, and I don't think I need to state that it's an element of the domain of f, because I'm about to find my my critical value, what I think might be the location of an absolute minimum. Because I think that when I do linear function minus this radical function, the linear function actually is going to be growing faster. So for a while, I'm going to be subtracting more than what I'm starting with. But then afterwards, I think I'm going to be subtracting less. So I'm hearing some sort of turning point going on here. Let's see if we can figure out where that turning point exists. F of 1/4. And notice I don't see the need to use a calculator here or any decimals here. The question didn't ask me to do any sort of approximate values. So why would I bother approximating? Students sometimes try arguing, you didn't tell me to get the exact values. And I would say, well, I also didn't tell you to approximate. So what do you think would be best to do? 1/4 minus 1/2. Let's try 1/4 minus 2/4. That's negative 1/4. Have I proven sign change? Not really. It didn't ask me to. Directions didn't ask me to analyze the direction. I think if we start recording this information on a sketch, let me just start here to specify or to clarify why I'm not doing a sign analysis now. I know this function exists at 0, 0 and 1, 0, and I now also know that it exists at 1/4, negative 1/4. So I'm pretty confident in the fact that we have a turning point there, because my domain is unrestricted there. It can't be a cusp, because I know I've got a root there. Yeah, I'm pretty sure then that I've got a turning point at 1/4, negative 1/4, and that this is the absolute minimum of my function, negative 1/4, of course, because minimums are values, not points. Fine. Now, what I'm wondering about here is concavity, because I kind of feel like I haven't had to inflect, but I'm not 100% sure of that. And this is where I'm going to go back to this line here and say to my reader, say we're working from asterisk 2. I guess you could get rid of the asterisk and just call the label 2. Let's look at our second derivative. F double prime of x is going to be 0 plus 1/4 times x to the exponent -3/2, -1/2 minus 2/2, -3/2. Let's tidy this up for analysis purposes. 1 divided by 4 times the square root of x cubed. Now we've got a discontinuity on our second derivative, but I'm not really interested in seeing if there's a sign change. I can tell that x cubed would change sign. I don't think the square root of something is going to change sign. Then I feel like, well, I mean, yeah, we can just look at this square root symbol right here and say that output is never going to change sign. There's no sign change. In fact, you could, if you're asked to look at concavity, you could just say, listen, the second derivative is going to be positive when x is greater than 0. I'm not going to discuss the concavity at an endpoint because you're not curving to the left of that point. In this case, it's because I do have a vertical tangent there as well. Okay. If there's no sign change, specifically over the domain of f, then there's no inflection points. So this rough sketch is actually going to turn out to be a decent final sketch. I don't want you stressing out too much about the scale. I think we could do an okay job with the scale here. If you put 0 there and 1 there, there's nothing really that interesting happens after 1. It wouldn't be a terrible idea to try to get 1/4 roughly where it belongs on the x-axis, but on the y-axis, you do not need this to be a square scale. And I think that putting 1/4 comma -1/4 on a square scale right there is going to make the curvature kind of wonky. So I'm just going to exaggerate this down here and say, look, we are going to be vertical there. I'm going to stress that vertical nature. Coming around to here, stationary there, and turning there. We've just got a root at 1. Nothing much else interesting happens. Let's just make sure that we draw our curve so that it doesn't ever look linear. You need to curve more or draw less. Let's make it very clear there's an end point here. Make it very clear there's no end point here. Let's make it very clear that this is the point 1/4 comma -1/4. And let's make it very clear that this represents the infinite number of points in the set of ordered point pairs that we call F by labeling it. And there you go. It doesn't need to be a complicated curve, but a full analysis will still take plenty of work. Okay, I like this for quiz or test level because it's a function that we might not feel super comfortable with without using calculus. A curve that we could draw without using calculus doesn't sound like a good calculus question. Okay, it's okay if you don't know exactly what it looks like right from the start. You have to use your tools to figure that out.